Welcome, everyone. Grab your notes if you're tuning into this explainer today. It means you are serious about the future of material science. I'm thrilled to be guiding you through today's session, where we're going to look at exactly how Portugal's textile and footwear industries are completely revolutionizing green engineering. And listen, we aren't just talking about minor sustainability tweaks here. No, we are talking about a fundamental transformation, taking agricultural waste, specifically from chestnut and olive harvests, and engineering it into high-performance biocomposites. It's absolutely fascinating. So let's dive right in. We're going to unpack the exact chemical and mechanical innovations that are literally replacing synthetic fossil fuel-based materials with advanced natural fibers.
Here is our syllabus for today. First, we'll cover Portuguese industrial symbiosis networks. Second, chestnut waste, focusing on polymers and dyes. Third, olive waste, looking at composites and tanning. Fourth, we'll do some direct chemical and mechanical comparisons. And finally, we'll wrap up with economic viability and transfer.
All right, Section 1, Portuguese industrial symbiosis networks, structuring the circular bioeconomic.
So, as engineering students, you know that true sustainability requires systems-level thinking. It's not just about isolated one-off material swaps. We're talking about a circular bioeconomy, an industrial model that replaces fossil fuel resources with local, renewable biomass. Now, I want you to really focus on that word, local. Instead of importing supposed eco-materials like bamboo or coconut fibers from halfway across the globe, which, let's be honest, carries a massive carbon footprint, Portuguese manufacturers are utilizing regional, non-seasonal agroforestry byproducts. By keeping the biomass sourcing domestic, they are drastically cutting Scope 3 emissions and transportation costs. It's an incredibly efficient, localized loop.
Now, a massive systemic shift like this, it requires serious capital. Two monumental consortia are driving this forward. First, we have BSET, commanding a massive €100 million budget and uniting 54 organizations under the leadership of CITEV. Parallel to that, we have BioShoes for All, operating with a €62 million budget and 70 partners coordinated by CTCP. And what's their shared goal? To accelerate the industrialization of bio-based polymers. They are directly targeting the elimination of toxic, non-renewable inputs. This allows the European market to shift away from low-quality, intensively manufactured global goods. It's a real game changer.
And we really have to consider the role of these technology centers, CTEV and CTCP. In engineering, we often talk about the valley of death. You know, that tricky gap between a brilliant laboratory prototype and actual, real-world commercial viability. Well, these centers serve as the vital bridges. They provide the advanced prototyping facilities needed to scale up production, and they rigorously validate the chemical safety and structural integrity of these eco-designs, ensuring they're actually ready for the market.
Moving right along to Section 2, chestnut waste, polymers and dyes, specifically looking at micronization and phenolic chemistry. Let's look closely at both the mechanical polymer applications and the phenolic chemistry of natural dyes derived from the chestnut tree. Transforming agricultural waste into a luxury fabric, like Montero Fabric's Peel collection, requires a highly controlled industrial process. It starts with the mechanical peeling of the chestnut fruits. Then comes the absolutely critical step, the collection and micronization of the solid shells and bark. Basically, this waste is ground down into an ultra-fine powder. Why? Because compounding this ultra-fine powder with a biological polymer paste ensures the absolute homogeneous dispersion required for high-end upholstery. If the particles are too large, well, the fabric surface becomes irregular and fails quality control. Finally, the coated fabric undergoes a thermal finishing process. And the result of that meticulous manufacturing process? Get a load of this number. 400,000. That is the number of Martindale abrasion cycles the Peel collection can withstand. To put that into perspective for you, heavy-duty commercial furniture usually requires about 40,000 to 50,000 cycles. This chestnut biocomposite achieves almost 10 times that standard. It's an exceptional physical performance that easily meets the strictest furniture industry standards, proving once and for all that biomaterials absolutely do not have to compromise on durability.
But, durability is really only half the story here. So, what does this all mean for functionality? How do natural chestnut extracts provide permanent antimicrobial properties to textiles? We've covered the mechanical side. Now let's pivot and talk about the chemical functionalization.
The answer to that lies in the incredible bioactive chemistry of the chestnut. The extracts contain proanthocyanidins, which are essentially condensed tannins. These phenolic molecules form highly stable hydrogen bonds directly with cellulosic fibers. Now, why should we care? It means we do not need to use synthetic, heavy metallic mordants to fix the dye to the fabric. Plus, spectroscopic analysis shows these compounds have a maximum UV absorption at 270 nanometers. This grants the textiles a permanent, natural barrier against UV radiation, right alongside robust antibacterial and antioxidant effects. It's just chemistry working brilliantly in our favor, and the whole shebang is entirely biodegradable.
Actually, a quick, vital semantic distinction here for you as future professionals in this space. Do not confuse Tintex textiles with Tintex dyes. Tintex Textiles is the advanced industrial manufacturer in Portugal that developed the highly complex color-round natural dyeing process we just discussed, successfully replacing petrochemical dyes for high-end fashion. Tintex dyes, on the other hand, well, that's just a commercial brand of domestic dye sachets meant for home washing machines. One is a marvel of industrial bioengineering, the other is a consumer craft product. You got to know the difference so you know exactly what scale of technology you are specifying.
All right, Section 3, Olive Waste, Composites and Tanning, focusing on saccharidoids and bio-based polyurethanes.
When we talk about bio-content, we simply cannot rely on marketing claims. We need hard data. That's where ASTM D6866 comes in. This is a rigorous radiocarbon dating verification method. Montero Fabrics used this exact scientific method to prove that their new Origin collection, which, by the way, utilizes micronized olive stones, genuinely contains 72% bio-based carbon. In an industry that is unfortunately rife with greenwashing, this level of strict scientific verification is exactly how you prove actual environmental impact.
And the technological maturity of these olive stone composites? 9. As in technology readiness level, or TRL, 9. Listen, this wasn't an overnight success. It took 8 years of intense laboratory testing across over 16 different bio-waste sources to reach this point. TRL 9 means the technology is fully mature, it's proven in an operational environment, and it's actually being utilized right now in the manufacturing of luxury sneakers. This is real, scalable industrial innovation in action.
But the olive tree's utility doesn't stop at the stones. Let's look at the eco-friendly tanning process for footwear, utilizing what's called wet green technology. By using aqueous extracts from olive leaves, which is a massive agricultural byproduct over there, this process completely eliminates traditional chrome-3. That removes any risk of it oxidizing into toxic chrome-6. Furthermore, by replacing synthetic tanning agents, or syntens, it drastically reduces the presence of bisphenols A, B, F, and S, all of which face severe EU restrictions. And remarkably, it still achieves a stable thermal shrinkage temperature of 80 degrees Celsius. It's a 100% biological leather alternative that drastically reduces environmental toxicity without sacrificing a single drop of performance.
Moving on to Section 4, Chemical and Mechanical Comparisons, Chestnut versus Olive. Okay, let's look at the data. When comparing the Peel collection, derived from chestnut, against the Origin collection, derived from olive waste, we see two very distinct engineering profiles. The chestnut composite boasts that incredible 400,000 martindale cycles, making it the ultimate choice for heavy-duty upholstery. The olive composite hits a very respectable 150,000 cycles, perfect for luxury footwear. Chemically, chestnut relies on polyphenols and tannins that create those stable hydrogen bonds with cellulosic fibers. Olive waste, however, is rich in secoiredoids and hydroxytyrosol, utilizing a natural ionic affinity for cationic textile substrates. So we have two completely different organic sources, two distinct molecular binding mechanisms, but both result in elite industrial materials. And get this, the biochemical properties of the olive waste go even deeper. Recent research out of the All of Us Text project demonstrates selective anti-proliferative properties. What that means is they've been shown in lab settings to eliminate HT29 human adenocarcinoma cells, a type of cancer cell, while maintaining low cytotoxicity for healthy cells. It's incredible. So replacing synthetic chemicals with these specific bioactive compounds doesn't just reduce environmental toxicity, it actually introduces deeply fascinating biological benefits right into the textiles themselves.
Finally, Section 5, Economic Viability and Transfer, Scaling the Bioeconomy.
Now, as engineers, we know that technical brilliance means very little if it cannot scale in the real world. So let's look at the economic reality of adopting these biomaterials. Montero Fabrics, a company founded over a century ago, realized the incredible market potential of their bio-coated fabrics. Confronted with instability in the automotive market, they successfully pivoted. Today, the lucrative luxury furniture and contract sector makes up 60% of their strategic focus, completely upending their traditional reliance on automotive textiles. It proves that embracing high-performance agricultural waste isn't just an environmental imperative. It's a highly viable, highly competitive market strategy.
Which brings us to our conclusion for today. Technology centers like CTIV aren't just developing these materials in a vacuum. They are working tirelessly to standardize them across Europe. This standardization is exactly what empowers manufacturers to outcompete cheap, low-quality, high-pollution production models. So I leave you with this final thought to ponder as you step out of this class and into your careers. How will standardizing these TRL9 biocomposites redefine the baseline for global textile engineering? The shift has already begun in Portugal. Now it's up to you to push it further. Thank you for joining me on this explainer today, and keep engineering a better world.